Part 4, you will hear part of a lecture about how scientists monitor active volcanoes. First, you have some time to look at questions 31 to 40. Now listen carefully and answer questions 31 to 40.
Today we are going to examine how volcano observatories recognize unrest before an eruption. The basic problem is that an active volcano is partly hidden. Scientists cannot see directly into the underground system, so they look for surface signals that suggest magma is moving below. Those signals do not provide a simple countdown, but they can show that the system has changed from its usual background behavior. One important signal is a change in seismic activity. As hot material forces its way through rock, the rock may crack, producing small earthquakes. A few isolated earthquakes are not enough to predict an eruption because many volcanoes have background tremors for years. However, a rising pattern can be significant when it is close to the volcano and when it appears together with other signs. A second signal is ground deformation. This means a measurable change in the shape of the volcano. If material accumulates in a shallow reservoir, the surface may move outward or upward by a few centimeters, even though that movement is not visible to someone standing on the ground. Scientists are interested in the direction of the movement as well as its size. Modern observatories often use GPS receivers to record that movement. These instruments can measure small shifts in position over time. They are especially useful because they can operate continuously and send data back to a monitoring center, allowing scientists to compare today's movement with the normal pattern from previous months. Tilt meters are another part of the toolkit. They measure tiny changes in the slope of the ground. A tilt meter near a crater may record inflation before an eruption or deflation when material drains away from the summit area. The readings can change quickly, so they are useful during periods of unrest. Gas monitoring provides a different kind of clue. When underground material rises, gases may escape through vents or cracks. One gas that is carefully tracked is sulfur dioxide, because changes in its release can indicate changes in the supply of hot material below the surface. Gas results are most valuable when they are compared with earthquake and ground movement data. Remote observations are also important. Satellites can detect warmer surface areas, new cracks, or changes in the shape of a volcano across a wide region. They are particularly useful where ground instruments are hard to maintain, or where bad weather and dangerous terrain make field visits difficult. Monitoring is not only about lava. Aviation authorities pay close attention to volcanic ash because fine particles can travel high into the atmosphere and damage aircraft engines. Separate warnings may be issued for ash clouds, even when lava flows remain near the crater or do not appear at all. Another hazard is produced when loose volcanic material mixes with water. These fast-moving flows are called lahars. They can form during heavy rain or when snow and ice melt, and they may follow river valleys far beyond the volcano itself. A community downstream may therefore face danger even if it cannot see the eruption. The key point is that no single instrument gives a complete answer. Scientists combine seismic records, deformation measurements, gas data, and remote images. This makes eruption forecasting a matter of probabilities rather than certainty. A good warning system, therefore, depends not on one dramatic sign, but on several changes that point in the same direction and are interpreted by trained observers.
That is the end of Part 4.